Big data is yesterday. Fast data is now. FiloDB is a reactive columnar OLAP database that is built on Cassandra and Spark. Today's guest is Evan Chan, the creator of FiloDB. In our discussion today, we talk about the use cases of an OLAP data store. Evan explains how to tackle the problem of video analytics. If you've ever found yourself asking how a company like a YouTube or Netflix or Ooyala performs analytics on millions of users watching millions of videos, this episode is for you. By combining the database features of Cassandra with the data processing power of Spark, Evan created FiloDB to help solve this type of analytics problem. Before we get to this episode, let's hear from a sponsor of Software Engineering Daily who keeps the show running at high throughput. Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/sedaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/sedaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code. Evan Chan is a distinguished engineer at TupleJump and the creator of FiloDB. Evan, welcome to Software Engineering Daily.
Thank you very much.
Let's start from a high level. A quote that you have said is that big data is yesterday, fast data is now. What does this quote mean?
That's a great question. So it's just referring to, I think when the big data hype started, what everyone was doing was creating these files and putting them in, say, Hadoop, and processing them. And this took a while. There would be delays, and so after a day, you would get some results, or maybe in some cases, an hour or so. But the world is becoming more and more interactive. Like people want answers like right away, and so you're seeing the rise of stream processing and real time, right? So people want, it's kind of like Twitter. People, want to see responses right away. So this is referring to that. Just having the ability to process tons of data is not enough. We need to react to data quickly and to deal with streams.
So this problem space that's become super important in software engineering these days is this need for an analytical database that can query large volumes of structured big data, but can also query fast data that is constantly updating. This is sort of canonical of this big data versus fast data problem. Why are these two problems of large volumes of structured big data and the ability to query fast data, why are these two problems difficult to solve at the same time?
I think it's just that's a good question. So why is the problem of fast data and big data, solving them at the same time, difficult? It's sort of like who is that? I'm blanking out a moment, but you know what they say, like when you try to measure, like in physics, you try to measure something. Really,
Heisenberg's uncertainty principle.
Yeah, that's right. The uncertainty principle. It's kind of like that, right? So the more that you try to focus on one thing, it's harder to do another thing, and it's sort of like that, right? Like the frameworks that are, well, at least when you look at it at a high level, the frameworks that process data with the really low latency are designed for low latency and not so much for throughput. And the other way around. So for example, Hadoop is typically architected for throughput. It's designed to load tons of data at the biggest volume possible. and Spark kind of comes from that tradition as well, but it's edging towards the streaming world. On the other hand, if you look at all the frameworks that process data in the streaming way, well, if you look at the extreme example are like, say, financial trading systems, right? Those are done like very, very specifically for super low latency, and everything is oriented around that. And so typically they focus only on a few really simple computations, right? Like the sums and things like that. And then you move on to systems like Scala and Akka, which is again like message processing, and you can have like a bit more state, but it's still like really oriented towards one message at a time. And systems like Apache Storm, so now there's become a continuum. But typically those systems are just designed for different things than the batch systems. But the really neat thing is that if you think about it, you can think of them as sort of there are definitely similarities, because you can think of a batch system as a streaming system of sorts, in a sense that I'm reading data from disk. I am really and that's a stream. So there's actually some overlap. So you can actually approach from the streaming side and say, I can build something batch, based on a streaming model and try to make that work. So it's actually not really opposed, but they're just systems are designed for different goals.
Interesting. So one example that you've given that describes this problem, this fast data and large structured big data, this canonical example you give is this video analytics problem. And I think it would make a good reference point for an example. So like a company like YouTube or Netflix or Ooyala would have this problem where millions of users are watching videos throughout the day, and their interactions with the videos are giving off just billions of events. And as some sort of data analyst, you want to be able to do analytic queries on all of the data, including the fresh data. So what are the requirements for a system that can do this?
Yeah, so I think you've actually stated some of those with your requirements already. You want to be able to look at fresh data, but you want to be able to analyze data that's been in the past. Let's look at, there's several. So if you look at the people who are most interested in consuming this data, they might be looking at different windows of time. Like they may be looking at the most recent, and then they want to look at the more historical point of view. For someone who is and they want to see the same, like they want to see similar types of data. Like they don't want to go to one system for the new data and another system for the old data. So for the engineer's point of view, you have to find some way of having a unified view of the new data and historical data. And there's different ways of doing that. There's been a popular term in the big data world called the Lambda Architecture, where folks have tried to solve this problem by having what is called a fast pipeline that approximates recent data. And then there is also a batch pipeline that deals with historical data, and you try to merge the two views. So that's been talked about a lot and floating around.
Right. And before we go any further, could you define the terms OLAP and OLTP? Because I think those are relevant to the conversation.
Oh, sure. Yeah, I think that's fine. So OLTP is online transaction processing, and the OLAP is simply switching the T for an A, which is analytical processing. Basically, let's put it in more simpler like layman's terms, right? Sure. OLTP, you can think of it as like, let me build Amazon. Like, let me build like millions of shopping carts, and I want that to work really, really well, right? So your goals in that case are, I want a lot of availability, and I want to be able to like update these shopping cart, like have millions of like updates like happening all the time, right? To someone's, say, shopping cart or profile or something like that. Whereas you can think of OLAP as maybe now I have all these shopping cart transactions. Someone wants to analyze them later and figure out, what are the trends? So instead of updating like one user's data at a time, like millions of times, you're looking at going through millions of records like a few times. So it's a very, very different emphasis.
So this video analytics system that we're kind of discussing, this would be an OLAP system.
Yeah, that would be an OLAP system. It's ingesting a lot of data and analyzing it.
Prior to your work on FiloDB, what were the options that were available to build this type of OLAP system?
Well, I'll describe the approach that we had taken at Uyala, for example, for video analytics. What we did is we would ingest the files into, say, Hadoop, and they would collect tons of data. Then we would run Hadoop batch jobs to crunch this data and take the raw data and compute aggregates with it. And this would then get saved to Cassandra. And then Cassandra becomes a good database for reading point values for dashboards. So we would basically store different breakdowns in Cassandra and serve it to people that way.
Do we need a database abstraction for this type of purpose that has both fast read and write capabilities, or do we just need like fast reads, or what exactly do we need from our database?
Yeah, I think that's a good question. I mean, if we go back in history, not even that far, to look at the traditional databases, the MySQLs, and then at more of the analytical databases like the Verticas, they actually had this capability, like of you could write tons of data and you could read them quickly and do things, and they would update. But what happens is that a lot of those systems, well, MySQL is open source, and it's more transaction node database. It's not that fast for analytics. But if you take examples like Vertica, most of those types of systems were proprietary and closed source, and they most of them could not scale very well, or until I think that they've been able to scale more, but then it would cost a lot more. So what happens when Hadoop came out was Hadoop was designed for processing a lot of data, and but files. So as it's based on files, then you went from database abstraction to a file abstraction. A lot of people call Hadoop a database, but it's a file system with a processing layer on top, right? So what you get with a file system is that you get economical storage, which is very important, granted, for big data. But at the same time, file abstraction is very different, is a much lower level than database abstraction. So that's what folks have been working with. And then you also have the rise of NoSQL of databases like Cassandra and Mongo and all these, which seem like they're great for transactions because you can identify things by key value. But in terms of the economy of storing data and analyzing a ton of them is not quite the same, right? So you sort of have you sort of see the big data world being split into kind of these two different camps, and so what I see is a need to bridge the two worlds again.
So I think it's important to discuss Cassandra. Like you said, Cassandra is one of the models. You kind of discussed the massively parallel processing databases like Vertica, and then Cassandra. So I guess, what are the relevant features of Cassandra for listeners who have no idea what Cassandra is? What should they know?
So Jeff, I think the Cassandra. Let's see, where should I start? So Cassandra is it's been described in a lot of terms, but you can think of it as a distributed key value database. What does that mean? Think of actually the analogy I like to use is that it's like a spreadsheet. So think of Excel. You have rows and columns, right? in Cassandra, you can store like structured and semi-structured records, tons of them. It's distributed, meaning that you don't have to worry about sharding your data. You write your data and you define a data model, and Cassandra takes care of distributing all your data for you. It makes sure that the data is highly available. So those are really good things. But what the unique thing about Cassandra is that it's based on Amazon's Dynamo, and you can think of it as basically a spreadsheet where you have rows and columns, and the rows are called partitions. So you define a partition key that basically defines what rows are you going to have, and that will tell Cassandra, the database, how to distribute your data. And then each row in your spreadsheet is guaranteed to be on a single node. And then the columns are important because in Cassandra you can do range queries. So basically you define your data model as you choose your row axis and your column axis, and then that basically chooses how you can partition your data as well as how you can quickly access your data. Right. An example, like a classic example for Cassandra that a lot of people use it for, is time series. Right. Let's say that I have thousands of machines, right, and I'm storing data. So I might use the machine ID as what is called a partition key, kind of like labels of the rows, and that would Cassandra would distribute those writes as new data is coming in. They would populate different rows, one row per machine, and then what happens is that for your columns you would use a timestamp. So as new data comes in and the timestamp increases, it kind of, you can think of the spreadsheet as filling up more and more to the right. Right. And so what that means is that when I read data for a single machine, it's very easy because I look up the row that has the machine ID, and then I look up the range of times I want, and I pluck out the data. And so for that use case, it's a very, very good fit.
And I think what you're getting at is that this columnar access pattern is effective for doing queries over large volumes of entries, where if you were thinking in terms of rows, if you wanted to get all the ages of somebody from a particular, all the ages of individuals from a row storage database, that would maybe be a more compute intensive operation than getting all the ages from a columnar storage. So it's conducive to this OLAP use case. Would you say it's accurate?
Okay. Let me. Okay. Sorry. Let me go back a little bit. So
okay,
it's not quite like that. It's more that. Let me see. What's the best way to put it? Basically, it's like this. Cassandra is not like a regular database like MySQL. It has very limited indexing capabilities. So the way that you model your data for fast reads, like in a traditional database, I would say, you know what, I need to access by column A or column B. So I'm going to throw an index at it. Then the index is going to let me pick at just the data I want. Cassandra is a little different. It does have secondary indexes, but they're not very effective. So the way that most people work is that we build models. Basically, the reason why I said spreadsheet is because you think of looking up Cassandra data in terms of like, I want to access this row of data and these columns from it. And when I say columns, I don't mean like columns as in like I have a record and I want first name, last name. What it is you can just think of a spreadsheet, and you can arrange your data in two axes. Then I can access the data by any one of the two axes very fast. Any other access pattern is probably going to be pretty slow. And then the other thing I wanted to clear up as far as columnar access is Cassandra actually is like row-based in terms of the storage. If you use regular Cassandra tables, so let's say that you have first name, last name, age, I don't know, ID or something like that, you'll find that those are always stored together in the record. So if you have a lot of, let's say that you come from a data warehousing background and you're dealing like typical OLAP, like you might have fact tables that are hundreds of columns pretty easily. Those 100 columns will be stored together. So if you wanted to pick out 2 columns out of the 100, it will actually be very slow because it has to read back all those records and it has to jump from, let's say you want first name or age, right? Then it has to jump to the age in every record. So in that way, it is actually like Cassandra is like a regular row-based database in terms of the storage layout. But unlike a database, it doesn't have very performant indexes. So the big difference is that you need to model your data very differently. You can't just dump your data and add a bunch of indexes. You need to maybe create 3 or 4 tables that have the X and Y axes modeled according to how you're going to query. And that's traditionally how you get very fast performance out, is that you have to do different kinds of data modeling.
Okay, so given that, what do we need to augment? Much of your the talks I've seen you give is about augmenting Cassandra with other functionality that would allow it to be good enough as the data store to provide this type of OLAP analytics service. Right. So what do we need to augment Cassandra with in order to provide this type of analytics?
Well, I think what you notice about Cassandra, for those of us that we've used it for a long time, is that if you really, Cassandra lets you store anything you want. So it does have the native CQL syntax where you can define tables and say, these are my columns, but you don't have to use it that way. And most of us that have used Cassandra for a long time, I've used it since it was, in the 0.6 days, several years, seems like ages ago. And the way that we modeled data was that we just decided how we're going to store it so that it's efficient. So, for example, you can store a blob, right? You can store let's say you have 20 fields. You can store it as a JSON blob, right? And then you can read that out, and you might find that to be more efficient than the regular way of storing it. So we play with a lot of these things. That Uyala, for example, would store data as thrifts blobs because it's very compact and reads very fast. So these are the things that we're used to playing with. So what I thought was, columnar storage is great because for analytics, you really want to pull out only the data that you need. And it gives a lot of advantages because you could easily, if you think about it this way, compressing whole rows is not actually that efficient because you kind of, the data that, it's easier to compress data when data is the same type of data is next to each other, right? Let's say I have 1,000, or let's say I have 1 million integers, and I know something about those integers, I can actually do a much better job of storing that in an efficient way than a whole bunch of mix of different kinds of data. And so those are the 2 key observations, is that in order to make analytics use case fast, where I usually read only a small portion of the data, small columns, I store the columns together. So that's the first thing. So I store, let's say I have 1 million rows, then I store all the data for first name together, and I store all the data for last name together, and age and so forth. And then you apply certain kinds of columnar compression techniques, like something like dictionary encoding for strings. It's the observation that you might have 1 million names, but there aren't 1 million unique first names. There's maybe, I don't know, say 10,000, right? So what you can do is you can map the 10,000 strings to numbers and store numbers, which is a lot more compact. So when you combine those techniques, then you end up with a storage format that can read out, that can store data much more compactly and read out a lot less of it. The benchmarks that I've done, which is based on public data sets, show that FiloDB is about, it really depends on how your data structure, but for, say, a data set that's about, say, 60 columns wide, the space savings is about 7x in the storage front alone. And if you combine that with being able to read only the columns that you need, then you end up saving a lot on I/O and having much faster reads.
Your company has important projects that need to get done. The iOS app needs to be rewritten for Android. The database needs to be migrated. Your continuous deployment system needs to be built. The website needs a complete redesign, but you don't have enough software engineers and designers to get all this work done. TopTal is here to save you. TopTal gives you exclusive access to the top 3% of freelance talent. Software engineers and designers from Python to PHP. TopTal has the freelance talent you need to get your projects finished on time with top quality. In the past, we had to worry about flaky freelancers with poor communication skills, unreliable internet connections, subpar technical skills, and so on. TopTal screens for these kinds of things and only works with seasoned professionals with tremendous problem-solving skills, personality, and drive. Here's how it works. TopTal's internal team of senior engineers will work with you to understand your project scope and your talent needs, and they will custom match you with just a few hand-picked candidates. This means that whenever you need to add top-shelf talent for a critical project, you can be connected with pre-screened engineers who are hand-picked for your needs. And the results are impressive. TopTal clients conduct just 1.7 interviews for every hire that they make. All you need is to come ready with some decent technical specifications of your project, and TopTal's team of engineers will take care of you from there. If you are looking to add critical talent fast and you need a source you can trust, go to toptal.com/sedaily. You can also send me an email directly at softwareengineeringdaily@gmail.com, and I will personally introduce you to the team at TopTal so that you can learn more. We live in unique times. The nature of work is changing, and more industry-leading companies from Airbnb to JP Morgan are realizing the benefits of scaling quickly and staying flexible by working with elite freelancers. So if you're short on resources for your projects, check out toptal.com/sedaily. Thanks to TopTal for sponsoring the show. Now let's get on with this episode. So this brings us to Spark. Why is Spark a good companion for Cassandra?
That's a good question. Well, so Cassandra, because traditionally Cassandra hasn't, Cassandra allows you to do simple reads, right? So you can look up data, but traditionally, like you haven't been able to do aggregations, you haven't been able to do joins, this kind of thing. So Spark brings a lot of deep analytical capabilities in terms of more complex queries for OLAP, but it also brings other things like machine learning. You could read stuff out and do regressions and compute models. So it brings like huge toolbox that you can analyze data with. And besides analytics, the other use case that folks have found useful for Spark is just as a ETL tool and as a tool for moving data around for doing administrative jobs. Folks have found that to be a good use as well.
You've also said that we can think of using Spark as Cassandra's cache. Can you explain what you mean by that in more detail?
Oh, definitely. So if you think about the different layers of caching, the Cassandra database there is the bottom. Cassandra itself has some caching, which is before you access. Basically, it comes before the network, but between on the server side. So there's server-side caching, and then you can cache in your client. Well, Spark is sort of like client-side caching in that you can cache data after you read from the network in memory, and that offers a huge performance benefit because you don't have to go through the network to get the data. So what it would look like is that, let's say your data is static, then you can cache the data in Cassandra as a, so Cassandra has, you can cache the data in Spark. Spark has SQL, SQL data frames, and those can be cached in memory in an efficient format. So then you can do something like cache table. And then the next time you read a table from Spark, it will cache it in memory. Then you can read it back much faster. And the ability to cache data in Spark is one of the things that's made it very famous and very well suited to things like machine learning and iterative algorithms. Yeah.
So I think this brings us to FiloDB. And FiloDB is a reactive columnar OLAP database that is built on Cassandra and Spark. I'd love to get a high-level overview of how FiloDB works.
Sure. Let's see. High-level overview. We'll try to figure out how to do this on audio.
We'll have videos in the show notes.
Oh, okay, cool. That sounds great. So let's see at a high level. So you have Cassandra and Spark, and you can think of FiloDB as a layer in between Spark and Cassandra. Cassandra, by nature, has its own table format, but you can think of FiloDB as a translator. It takes the data from Spark and translates it into columnar format, then writes it into Cassandra. And on the read side, it does the same thing. It has a Spark data source that reads out the data, the raw chunks from Cassandra, and translates it into rows that Spark understands and can do complex analysis on. At a 30,000 foot view, it's sort of like that. And in the ingestion path, FiloDB has a mem table like Cassandra, but it's optimized for columnar storage. So ingest a lot of data into memory and chunk it up and then write it to Cassandra.
So perhaps this would be easier to explain with an example. Well, maybe not, but hopefully this will be easy to explain with like an example. Like if we go back to that video analytics example, maybe you could explain how FiloDB would be an appealing option for, from ingestion to analytics, kind of what that would look like.
Oh, yeah. I think that's I think that's a good idea. So we'll back up to, so let's say that your system let's say your data is coming in through a message queue, right? That's these days it's most likely to be Apache Kafka, and then it would go into some processing system. Then you write it to somewhere, like you might write it to Hadoop, or you might write it to, say, raw data in Cassandra. So where FiloDB will fit in is that basically it could sit in as where you ingest your raw data. So you would have data from Kafka coming into, say, Spark Streaming. Then Spark Streaming would take the data, which is already partitioned, and write it into FiloDB. And the difference. And so you can think of FiloDB as a much more performant substitute for writing into Cassandra. You could model your data in a similar way. Let's say for video analytics, I might divide my data into, say, some timestamp and customer ID, kind of thing. Or there's other ways of dividing it, like, but you have some key, and I could write the data into it. The contrast is, so the way that I would think about it is that it's like writing into Cassandra, but it's more performant for writes as well as reads. And it's unlike Hadoop in that I'm writing data using a primary key. So the really nice thing about it writing into a database as opposed to a file is that your systems are never going to work 100%. At some point, Spark Streaming, which is getting more mature, but it still crashes once in a while. So let's say that Spark Streaming crashes, right? So you have to plan for this. Now you need to figure out, okay, I'm going to restart Spark. And if you're writing to a file, you're not quite sure. You've written data at some point, and then you need to go back and you need to replay this data, right? So what happens when you replay data? So Kafka is designed, is very good for this because it buffers up data. Then you decide at some point you failed, so you have a checkpoint. You're going to go back to your checkpoint and replay all the data. With the files-based system, when you replay this data, it's going to get appended, or at least to HDFS it will get appended. Then later on, you're going to need to run jobs to deduplicate the data and make sure. For some people might not need this, but for a lot of people, you don't really want to count things twice, right? So you need to go back and deduplicate data, which is pretty expensive. With a database based system, when you write into primary key, you know that you're going to overwrite the same data, so that you won't have the problem of deduplication.
So there's a lot there, and I want to delve into, now that we have like a higher level overview, we've covered some of what FiloDB is. I want to drill down into some of the closer up features. So FiloDB has a parquet-style storage layout.
Right.
Could you explain what that means?
Yeah, so what it means by a parquet-style layout is that we're following the same principles in terms of that Parquet uses. That is that we group data by columns. And so when you have 1,000 rows, we're going to store all the 1,000 points from one column, like first name, together. And then we do that, and data is grouped into in Parquet is grouped into pages, and FiloDB is grouped into partitions. So it follows a similar layout that groups data together by column is what is meant there.
Got it. So, and I think we've already kind of covered the advantages of the columnar format. So another feature of using this is that Cassandra is a versioned database. Why is this a desirable feature given the use cases for FiloDB?
Yeah, let me clarify that. So there's some versioning built into FiloDB. Cassandra by itself is not necessarily a versioned database, although you could implement it yourself just by adding a version key. So versioning, I guess that depends on who you talk to, but I'll describe some use cases that inspired the versioning, and it's that one is that for some use cases, you want to be able to control what data that the user sees. This is especially true in, say, government data or like highly sensitive, like, say, public data sets. Let's say that you have a data set that it has, say, public official salaries or something. And let's say that this got updated and you made a mistake. That would be like pretty bad, right, to publish something like that. So usually in these kind of environments, the versioning is very important in the sense that I want to be able to add some changes and I want to be able to preview it. So you can think of that as like transactions in some ways, except that for most databases, like the transactions are not designed to leave data like in different versions, so to speak. They're more designed so that you can roll back your changes. But if I was to write data to a regular database like MySQL, you would still see the update pretty fast. You could roll it back with a transaction, but versioning is more like I can write the data, I could have it for like a week, in a new version and not like merge it until I'm ready. So it's more about user control over what you see.
So we hear a lot about the Lambda architecture these days. And I know you've taken some umbrage with this term, but you've also said that FiloDB can simplify a Lambda architecture. Could you explain how you see the Lambda architecture today and why FiloDB offers a simplification?
I would say systems like FiloDB can simplify the premise of Lambda is that you need separate systems to process the fast data and the big data, and then you need to manage the complexity and merge it because the systems are designed for different strengths. And I think what FiloDB says is you don't really need separate systems. You need a well-designed system that can handle both well. And then you can eliminate the complexities. For example, let's say that I'm a shop running Cassandra, and there's a lot of those. And I want to add, big data analytics. I don't have to add an entire Hadoop infrastructure. I can, and the converse could be said about someone who's running only Hadoop, but not needing to add, a NoSQL store. Basically, I could stick with one system, one set of systems that can do both jobs instead of needing to implement both and merging data from both systems. So that way you have the same system that you use. For example, I could use regular Cassandra for dashboards, and that would work very well. And this way I can use Cassandra also for analyzing a lot of data. And so that way, I only need to maintain one set of technologies, and instead of having to maintain several. And I think that's quite appealing from TCO perspective.
And at Strata plus Hadoop World 2016, you're giving a talk called No Lambda, a new architecture combining streaming, ad hoc, machine learning, and batch analytics. So what are the tenets of this architecture, and what are we moving away from that we're leaving behind from the Lambda architecture?
Yeah, I think we just mentioned it, but basically you're talking about simplicity, having streaming systems that can flow into data storage systems that can handle it, that can process new data, old data, and stuff together, and having a much more simplified stack that can do, you can get a lot more out of one stack, as opposed to needing several. And I think that's really the main word is kind of like the simplicity and using the same things for both.
What kinds of technologies would we want to have in this no Lambda stack?
I mean, I talk about the technology stack that I'm familiar with. That we'll be talking about consists of Apache Kafka, Spark, Cassandra, Scala, and Akka, and I think that will fit all these use cases for streaming as well as for batch analytics when you add in something like FiloDB. That's obviously not the only stack you could have. There are other ones out there, but that's the one that I'll be describing.
So this is the SMAC stack.
Yes, that's right. Yes.
Okay. So the SMAC. So this includes some technologies that we haven't really discussed yet, and I'd love to get an overview of this architecture. So, for example, how does why is Scala and Akka so appealing that you would fit it into the acronym SMAC?
Okay, all right. So SMAC stands for Scala, Mesos, Akka, Cassandra, and Kafka. Actually, it's not just Scala; it's Scala and Spark. That's so the S is quite a big letter in that, but it's the first one, so
true.
That's okay. So why are these technologies a good fit? I mean, because they encompass all the different needs. Like if we start with Scala and Spark, why is Scala important? One is, I think, for two things. One is because it is tied to the JVM, where you have so many big data technologies, and as a platform is pretty crucial. But at the same time, it offers functional aspects, which has been, I think, a really big key of Spark's success. Is that the idea that in Scala, I can have collections, I can have a list of items, and I can transform them, sort it, and map it into other things to produce new values. This is like a very key part of functional transformation and functional programming, instead of like thinking about procedurally going over one thing at a time, right? I think that's been really crucial for Spark's success, because not only because Spark's written in Scala, but conceptually, for me, transforming a collection in Scala is the same as transforming a RDD in Spark. It's really this not only conceptually the same, but many of the transformations are named the same thing. Doing a map and doing a group by, right? And so once you get this concept, then it really you can transform any kind of data that way. So it becomes very, very powerful. And just quickly, it's really hard to fit the description of the whole stack in 2 minutes, right? But I think Scala, Cassandra, we've talked about. Kafka, because you need a way to ingest data in a streaming environment. Spark streaming can transform it. And where the Mesos and the Akka parts that we haven't talked about come in is that Akka is important because it offers a very low latency framework for handling data in a message-driven reactive way. And that sounds really loaded, but for a big data pipeline, there are times when you need connectors for just to, let's say you need a way to ingest data through HTTP, right? So Akka is an HTTP module, right? And Scala has a lot of HTTP frameworks. And Akka is really good at handling failure and at getting your data. Like if you need data to flow in milliseconds, you're probably going to be doing that in Akka. So that becomes, that fills out the whole framework. And then Mesos is a way of, I think in any framework, you need a way of orchestrating different resources. And so Mesos is a, I mean, there's obviously a lot of different ones that Spark can work with, but Mesos offers a good way for to have different resources be mediated and to share those resources. And you can even have, it's not just for big data, right? Mesos can be used to run your microservices and to deploy them, to orchestrate them. So it's a pretty powerful tool set. So in this whole stack, you have a processing framework, which is Spark. You have storage system like Cassandra and FiloDB. You have the pipeline, which is Kafka. You have concurrency and low latency framework like Akka, and then you have an orchestration and operation framework like Mesos. So it kind of rounds out the whole stack.
So within that stack, we've talked about 2 out of 3 of the big Berkeley technologies that I've heard about recently. And the third one is Tachyon, which I've also heard you talk some about. We have an upcoming show with HY, who's the creator of Tachyon.
Yeah, that's right. Yeah.
So why I saw a talk where you mentioned Tachyon and why it's appealing to the Spark and Cassandra synergies. So why is Tachyon exciting to you and to FiloDB?
Yeah, I think Tachyon is going to be very important. As we talked about caching earlier, and the importance of like in-memory caching. So Tachyon is like a you can think of it as a highly available in-memory cache. So we talked about possibly caching data from Cassandra and Spark earlier in memory, but there's a couple weaknesses with that. It's one of the major ones is that it's not HA because the data is cached in a Spark workers heap, and so once Spark or any of its workers goes down, then you lose that data. Tachyon is different because Tachyon stores the data off heap outside of the Spark processes, but it has a way to enable you to read the data very quickly still. So it works very well as a cache, and I think folks that have found it very compelling are folks that are using it to store data that could be local or remote. So definitely for the remote data, you could get it much faster from Tachyon. So it kind of offers a tiered. You can think of it as a caching, offers multiple caching tiers, and so that could be very important to your architecture.
Is that speed of access by Tachyon, is that enabled by Lineages?
Lineages. Well,
or is that totally misunderstanding that?
Oh yeah, so the lineage thing. You're talking about lineage like in Spark?
Well, I mean, I've been like reading white paper about Tachyon and like kind of trying to understand, how to approach it in the interview.
Got it.
And I understand lineages are a big feature that are in both Spark and Tachyon. So I guess I was trying to understand. I guess what to know about lineages.
Oh, I see. Well, the way that I understand the term is that it's referenced in Spark is that lineage is basically a history. You can think of it as like recording how you get to a certain state, right? So instead of storing, say, 3 copies of my data, I'm going to remember how I got that data and assume that the origin of that data is stored in some, fail-safe or replicated store, right? And so if there's a failure, I can then go back and recompute the data that I need. So that's the concept of lineage. And I think when you apply it to Spark and Tachyon, in Spark, it kind of looks like basically RDDs are lazy, right? So if I get a result, that's good. If the result is lost, then I'm going to try to recompute that result based on the previous steps. And I think you can apply that to caching as well. If I'm missing some data, I can I can know where that comes from. the lower layers, and so I can recover it. So it's a slightly different. I think it's different and complementary to the XJ concept. The XJ concept is more like I'm going to have data that's available right away. But I think you can have both. And maybe in certain cases, that trade-off is, you can make some interesting trade-offs.
Interesting. Do you know what the hurdles are to Tachyon starting to gain adoption or integration? Is it just the writing of plugins, or what exactly do we need to take Tachyon to the next level?
That's probably a better question for HY. I mean, I'm sure you would say that it's already gaining traction. I think, and I know that they're working on like having more systems be able to plug into it. So it's probably just a matter of time, like other things.
Sure. So you're working on FiloDB at TupleJump.
Right.
What is TupleJump?
Thank you for asking. So TupleJump, we are a big data technology and services development partner. So you can think of it as we are here to help you. You meaning, say you are an enterprise or some other company that wants to develop certain big data platforms to support. We're basically there to help you, every step of the way to get there, especially in the early phases. And our architecture design, we're pretty strong at. But we also would do all sorts of projects. And especially if the area involves Spark or Cassandra, streaming, Kafka, this kind of thing, I think we can definitely help other folks along.
What kinds of products do you want to build in the future at TupleJump?
What kind of products? I mean, I would say
are you mostly focused on just delivering existing products and kind of the model of consulting and helping out enterprises, or do you want to continue to build out more products?
It's a hybrid of consulting and also building out our open source projects, which complements a lot of these big data development projects. So I think it's a hybrid model.
Interesting. So speaking more broadly, where do you see this space going? Like, what is at the frontier of this problem of big data meets fast data?
I think, that's a great question. What is at the frontier? I think a lot of it will be probably there's different aspects to think about. I mean, I think that there's, from a technology point of view, there's always performance envelopes and other things like that to push, to make things, faster, better. Although I think that a big part of it is that we're just getting started. I think this is a relatively new concept. Folks are very much, there are a lot of folks that are still on, say, data warehouses. They're kind of moving into this world and trying to figure it out. So I think that actually the frontier is more like education and applying it to specific verticals and use cases. So I sort of see it as, it is a frontier. And so what that means is that we need to bring it to folks and help educate and get the concepts rolling more.
Sounds like there's plenty of low-hanging fruit. Well, Evan, thanks for coming on to Software Engineering Daily. It's been really great talking to you about FiloDB and the SMAC stack and everything else that we discussed.
Yeah, Jeff, thanks very much for having me on the show. It was a pleasure.
Absolutely.